Section 9.2, the Vsepr model. Imagine tying two identical balloons together at their ends, as shown in figure 9.5. The balloons naturally orient themselves to point away from each other. That is, they try to get out of each other's way as much as possible. If we add a third balloon, the balloons orient themselves towards the vertices of an equilateral triangle, as shown in figure 9.5b. If we add a fourth balloon, they adopt a tetrahedral shape. We see the optimum geometry exists for each number of balloons. In the same way, the electrons in the molecules behave like the balloons shown in figure 9.5. We soon see that the single covalent bond is formed between two atoms when a pair of electrons occupies the space between the atoms. A bonding pair of electrons thus defines the region in which the electrons will most likely be found. We will refer to such a region as the Electron Domain. Likewise, a non-bonding pair or lone pair of electrons defines an electron domain that is located principally on one atom. For example, the Lewis structure of ammonia has 4 electron domains around the central nitrogen atom, 3 bonding pairs and 1 non-bonding pair. Each multiple bond in a molecule also constitutes a single electron domain. Thus, the following resonance structure for ozone has 3 electron domains around a central oxygen atom, a single bond, a double bond, and a non-bonding pair of electrons. In general, each non-bonding pair, single bond, or multiple bond produces an electron domain around the central atom. The Vsepr model is based on the idea that the electron domains are negatively charged and therefore repel one another. Like the balloons in figure 9.5, electron domains try to stay out of each other's way. The best arrangement for a given number of electron domains is the one that minimizes the repulsions among them. In fact, the analogy between electron domains and balloons is so close that the same preferred geometries are found in both cases. Like the balloons in figure 9.5, 2 electron domains are arranged linearly. 3 domains are arranged in a triagonal planar fashion, and 4 are arranged tetrahedrally. These arrangements, together with those of 5 electron domains, triagonal bipyramidal, and 6 electron domains, octahedral, are summarized in Table 9.1. If you compare the geometries of Table 9.1 with those in Figure 9.3, you will see that they are the same. The shapes of different ABN molecules or ions depends on the number of electronic domains surrounding the central A atom. The arrangement of electron domains about the central atom of an ABN molecule or ion is called its electron domain geometry. In contrast, the molecular geometry is the arrangement of only the atoms in a molecule or ion. Any non-bonding pairs are not part of the description of the molecular geometry. In the Vsepr model, we predict the electron domain geometry. From knowing how many domains are due to non-bonding pairs, we can then predict the molecular geometry of a molecule or ion from its electron domain geometry. When all the electron domains in a molecule arise from bonds, the molecular geometry is identical to the electron domain geometry. When, however, one or more domains involve non-bonding pairs of electrons, we must remember to ignore those domains when predicting molecular shape. Consider the ammonia molecule, which has 4 electron domains around a nitrogen atom. We know from Table 9.1 that the repulsions among 4 electron domains are minimized when the domains point towards the vertices of a tetrahedron. So the electron domain geometry of the ammonia molecule is tetrahedral. We know from the Lewis structure of ammonia that one of the electron domains is due to a non-bonding pair of electrons, which will occupy one of the 4 vertices of the tetrahedron. Hence, the molecular geometry of ammonia is triagonal pyramidal, as shown in figure 9.6. Notice that the tetrahedral arrangement of the 4 electron domains leads us to predict the triagonal pyramidal molecular geometry. We can generalize steps we follow in using the Vsepr model to predict the shapes of molecules or ions. 1. Draw the Lewis structure of the molecule or ion and count the total number of electron domains around the central atom. Each non-bonding electron pair, each single bond, each double bond, each triple bond counts as an electron domain. 2. Determine the electron domain geometry by arranging the electron domains around the central atom so that the repulsions among them are minimized as shown in Table 9.1. 3. Use the arrangement of the bonded atoms to determine the molecular geometry. Figure 9.6 shows how these steps are applied to predict the geometry of the ammonia molecule. Because the triagonal pyramidal molecular geometry is based upon a tetrahedron electron domain geometry, the ideal bond angles are 109.5. As we'll soon see, bond angles deviate from ideal angles when surrounding atoms and electron domains are not identical. Let's apply these steps to determine the shape of the carbon dioxide molecule. First, we draw its Lewis structure, which reveals 2 electron domains, 2 double bonds around a central carbon. 2 electron domains will arrange themselves to give a linear electron domain geometry. Because neither domain is a non-bonding pair of electrons, the molecular geometry is also linear, and the OCO bond angle is 180 degrees. Table 9.2 summarizes the possible molecular geometries when an ABN molecule has 4 or fewer electron domains about A. These geometries are important because they include all the commonly occurring shapes found in molecules and ions that obey the octet rule. The effect of non-bonding electrons and multiple bonds on bond angles. We can redefine the Vsepr model to predict and explain slight distortions of molecules from the ideal geometries summarized in Table 9.2. For example, consider methane, ammonia, and water. All 3 have tetrahedral electron domain geometries, but their bond angles differ slightly. Notice that the bond angles decrease as the number of non-bonding electron pairs increases. A bonding pair of electrons is attracted by both nuclei of the bonded atoms. By contrast, a non-bonding pair is attracted primarily only by one nucleus. Because a non-bonding pair experiences less nuclear attraction, its electron domain is spread out more in space than the electron domain for a bonding pair, as shown in Figure 9.7. Non-bonding pairs of electrons, therefore, take up more space than bonding pairs. As a result, the electron domains for non-bonding electrons exert greater repulsive forces on adjacent electron domains and tend to compress the bond angles. Using the analogy in Figure 9.5, we can envision the domains for non-bonding electron pairs as represented by balloons that are slightly larger and slightly fatter than those of their bonding pairs. Because multiple bonds contain higher electron charge density than single bonds, multiple bonds also represent larger electron domains, fatter balloons. Consider the Lewis structure of phosgene, COCl2. Because 3 electron domains surround the central carbon atom, we might expect a triagonal planar geometry with 120 bond angles. The double bond, however, seems to act much more like a non-bonding pair of electrons, reducing the chlorine-carbon-chlorine bond angle from an ideal 120 to an actual angle of 111.4. In general, electron domains for multiple bonds exert a greater repulsive force on adjacent electron domains than do electron domains for single bonds. Molecules with expanded valence shells. So far, our discussion of the Vsepr model has considered molecules with no more than an octet of electrons around a central atom. Recall, however, that when the central atom of a molecule is from the 3rd period of the periodic table and beyond, that atom may have more than 4 electron pairs around it. Molecules with 5 or 6 electron domains around a central atom display a variety of molecular geometries based on the triagonal bipyramidal or the octahedral electron domain geometries, as shown in Table 9.3. The most stable electron domain geometry for 5 electron domains is the triagonal bipyramidal, 2 triagonal pyramids sharing a base. Unlike the arrangements we've seen to this point, the electron domains in the triagonal bipyramidal can point 2 geometrically distinct types of positions. 2 of the 5 domains point toward the axial positions, and the remaining 3 domains point towards equatorial positions. Each axial domain makes a 90-degree angle with any equatorial domain. Each equatorial domain makes a 120-degree angle with either of the two equatorial domains and a 90-degree with either axial domain. Suppose a molecule has 5 electron domains, one more which originates from a non-bonding pair. Will the electron domains from the non-bonding pairs occupy axial or equatorial positions? To answer this question, we must determine which location minimizes the repulsions between electron domains. Repulsions between domains are much greater when they are situated 90 degrees from each other than when they are 120 degrees. An equatorial domain 90 degrees from only 2 other domains. By contrast, an axial domain is situated 90 degrees from 3 other domains, the 3 equatorial domains. Hence, an equatorial domain experiences less repulsion than an axial domain. Because the domains from non-bonding pairs exert larger repulsions from those of non-bonding pairs, they always occupy the equatorial position in a triagonal bipyramid. Figure 9.8, Triagonal Bipyramidal Geometry. 5 electron domains arrange themselves around a central atom as a triagonal bipyramid. The 3 equatorial electron domains define an equilateral triangle. The 2 axial domains lie above and below the plane of the triangle. If a molecule has a non-bonding electron domains, they will occupy the equatorial positions. The most stable electron domain geometry for 6 electron domains is the octahedron, as shown in Figure 9.9. An octahedron is a polyhedron with 8 bases and 6 vertices, each of which is an equilateral triangle. If an atom has 6 electron domains around it, the atom can be visualized as being at the center of an octahedron with the electron domains pointing towards all 6 vertices. All the bond angles in an octahedron are 90 degrees, and all 6 vertices are equivalent. Therefore, if an atom has 5 bonding electron domains and 1 non-domain, we can put the non-bonding domain at any of the 6 vertices of the octahedron. The result is always a square pyramidal molecular geometry. When there are 2 non-bonding electron domains, however, the repulsions are minimized by pointing them towards opposite sides of the octahedron, producing a square planar molecular geometry, as shown in Table 9.3. Shapes of larger molecules. Although the structures of the molecules and ions we've already considered contain only a single central atom, the Vsepr model can be extended to more complex molecules. Consider acetic acid molecule with the following Lewis structure. Acetic acid has 3 interior atoms. The left carbon atom, the central carbon atom, and the right oxygen atom. We can use the Vsepr model to predict the geometry about each of these atoms individually. The leftmost carbon has 4 electron domains, all from bonding pairs, and so the geometry around that atom is tetrahedral. The central carbon has 3 electron domains, counting the double bond as one domain. Thus, the geometry around that atom is triagonal planar. The oxygen has 4 electron domains, 2 from bonding pairs and 2 from non-bonding pairs, so its electron domain geometry is tetrahedral, and the molecular geometry around the oxygen is bent. The bond angles around the carbon atom and the oxygen atom are expected to deviate slightly from the ideal values of 120 and 109.5 because of the spatial demands of multiple bonds and the non-bonding electron pairs. The structure of the acetic acid molecule is shown in Figure 9.10.